Okay, so in this lecture we are gonna talk about a important ring theoretic concept. But before that, let me give some introduction to or some motivation to what I'm actually going to establish in this lecture. If you guys have studied elementary number theory, so let me be a bit detailed. So if you have studied elementary number theory, then there are a special class of functions which we talk about in case of elementary number theory, which are called number theoretic functions. And number theoretic functions actually deal with certain important properties of numbers. That is, they help us calculate some important properties of numbers, and some important examples being suppose calculating the number of factors of a number, calculating the sum of factors of a number, and one of the most important ones out of them is this number finding calculating the number of coprime elements below some number n, coprime elements to n below n, and this the function which calculates this value is what we call the Euler's phi function, or it's often called the Euler's totient function. And as the name suggests, we use the symbol phi. Okay. Now phi has some very well known formulas, that is phi of some prime p to the power some integral power of it is given as p to the power alpha minus p to the power alpha minus 1. And the proof of this is fairly from definition, that is, see, after all, we are calculating the number of elements which are coprime to p to the power alpha, right? So now observe that the elements which are coprime to p to the power alpha are precisely all multiples of p till p to the power alpha, because after all we are concerned about elements below n, right? So below p to the power alpha or less than equals to n, but n will, the number itself will obviously not be coprime to itself. So the elements which are coprime to p to the power alpha are precisely, I have written a statement wrong here. The elements not coprime to p to the power alpha are precisely all multiples of p till p to the power alpha. And how many are there? So you start with p, the next multiple you have 2p, then you have 3p, and you continue till you reach p to the power alpha. But this is a standard arithmetic progression. So how many elements are there? So the first element is p. Suppose you have n elements, so the common difference is p as well. So you have this, but this implies p times 1 plus n minus 1 is equals to p to the power alpha, but this implies n is p to the power alpha minus 1. Therefore, there are exactly p to the power alpha minus 1 elements which are not coprime to p to the power alpha, and till p to the power alpha we have p to the power alpha number of integers. So the elements which are coprime should be exactly equals to p to the power alpha minus p to the power alpha minus 1. So total number of integers till p to the power alpha, and we just subtract the number of elements which cannot be coprime to p to the power alpha, and we have our result, right? Sometimes it's also denoted as p to the power alpha minus 1 times p minus 1, whatever, these are exactly same. But the problem arises when we want to find the value of phi for any arbitrary integer, okay, where n is arbitrary integer. Now see, one should immediately follow this up from here, that since we know the value of the Euler's phi, the value of the totient function for a power of p, and we know that I can write n as a product of primes, right? So suppose I have n is equals to say p to 1 to the power alpha 1 till pr to the power alpha r, where each of these pi's are distinct primes. Then this implies that phi n is just the totient of each totient of this product, but this immediately does not give us any value, right? If in some way I can write this as phi of p1 to the power alpha 1 till phi of pr to the power alpha r, then I'll surely get a formula for n, for an arbitrary integer, because this will come out to be p to the power alpha minus 1, sorry, p1 to the power alpha 1 minus 1 times p1 minus 1, and the product you will have till, so here you have pr to the power alpha r minus 1 till pr minus 1. Now if you take p1 common from here, then p2 common outside from the factor p2 minus 1, and then pr common outside from here, then I eventually land into p1 to the power alpha 1, p2 to the power alpha 2 till pr to the power alpha r times 1 minus 1 over p1 and so on till 1 minus 1 over pr. But observe, this is nothing but n, and this is the most well known formula given to us, which is n times 1 minus 1 over p1 times 1 minus 1 over pr. But observe that we immediately are not sure about whether this is the exact formula or not, but indeed it is, but we exactly don't have the tools to give us sufficient proof of this, because if you carefully observe, the proof only lies in the fact that if I can distribute phi over product of elements which are mutually coprime. If you observe, two primes are always coprime, right? So powers of two distinct primes will also be coprime. Such functions are typically called multiplicative functions. Such functions are typically called multiplicative functions, multiplicative number theoretic functions, where, so let me just use phi only for the notations, where phi of AB can be written as phi of A times phi of B, where A and B are coprime, that is their GCD is 1. Okay. So if I somehow prove that the Euler's totient function is multiplicative, then there is nothing more to do, right? And what we will do in this lecture is that we will exactly prove the fact that phi is multiplicative in nature, but the twist is that we will do it in completely algebraic process and we will make use of rings. Okay. So let me just write the goal here. Goal: proving the multiplicative nature, of phi using algebra, or specifically using rings. Clear? And to do that, the theorem we actually require, which is also some sort of a generalization coming from elementary number theory, is called the Chinese remainder theorem. Is called the Chinese remainder theorem. So in elementary number theory, Chinese remainder theorem is basically solving simultaneous congruences modulo coprime elements. So we actually want to generalize that into in case of algebras. Okay. So how do we do that? Before doing that, we need an elementary notion of the direct products of rings. Now if you have studied groups, which you surely should have studied before moving on to rings, then I guess you people know how a direct product typically looks like. So in case of groups, we have two different classes of direct products, one we call the external direct product and one we call the internal direct product, but eventually we see that both are actually isomorphic, or in some sense you can also just state that both are actually equivalent of speaking. So if you talk about an internal direct product, then actually you are talking about an external direct product as well, right? Okay. So in this case we will define such a direct product, and we are not going to go into different notions or different definitions of that. So let's do it. But I think this is actually quite straightforward, that let R and R1 and R2 be two rings. Okay. Define R1 cross R2 to be the collection of elements of ordered pairs R1 R2 such that R1 small r1 comes from the ring R1 and small r2 comes from the capital ring R2. Okay. So, this is simply called a direct product, but for it to be called a direct product, since we are studying rings, it should have a ring structure. But the ring structure also immediately follows from the following operations. Define R1 R2 plus R3 R4 as R1 plus R3 R2 plus R4. That is basically we are doing component wise addition. Component wise addition. And we will do a component wise multiplication as well. R1 R2 times R3 R4 is just R1 R3 R2 R4. So, we are just doing here component wise multiplication. Observe that this immediately gives you a ring structure. The ring structure actually follows from the in each individual ring R1 and R2 itself. Clear? Now, what should be the respective units which can be usually exactly followed from the definition itself. So, 0 R1 and 0 R2 must be its additive identity, not the units, the additive identity, and 1 R1 and 1 R2 must be its multiplicative identity. In fact, the units, if I talk about units of R1 plus R2 are the ones where each component is a unit or each coordinate is a unit, right. Suppose I say that the element AB coming from R1 cross R2 is invertible. So, this means that there exists some element say CD such that it must equal the multiplicative identity 1 1, but this implies that AC and BD, so individually AC and BD will equal 1, but that implies that A must be a unit and B must be a unit respectively in R1 and R2, right. So, this point is important, we will make use of this later. Okay. Now, as I say in every lecture that most of the notions which come in the concepts of rings are sort of thought in the ring of integers or in the case of integers, and then we try to generalize that. If you follow in integers in Z, if you choose elements m and n to be coprime, then observe that mz plus nz must equal z. If you recall how used to we define I plus j for I and j being two ideals, so it just is the collection of elements a plus b, where a comes from capital I and b comes from capital J. And this is also actually following, so this is pretty trivial to observe, but this, since we have already studied Euclidean domains, this trivially follows from the Bezoar lemma. This trivially follows from the Bezoar lemma, because since m and n are coprime, I can write 1 as a linear combination of m and n. And since we are inside ideals, so ideals are closed under elements from multiplication by elements from R. So, I can choose any element from Z and I can multiply that to the linear combination, and on the right hand side we will get an arbitrary element from Z itself, and on the left hand side I will get an element as a sum of elements from MZ and NZ. So, it trivially follows up from here only. Okay, there is nothing too complicated there. So, we will generalize this to arbitrary rings, and this gives us the definition of what we call co-maximality. So, let R be a ring, let R be a ring, and let I and J be ideals of R. We say I and J are co-maximal we say I and j are co-maximal if I plus j equals r. Clear? So in case of Z, if I talk about the principal ideal generated by coprime elements, I'll eventually land into co-maximal ideals. Clear? Got it? Okay. Now this actually gives us what we call the Chinese remainder theorem, and we need no more tools to prove that. So the Chinese remainder theorem, So what does the Chinese remainder theorem basically says? So we start with some n ideals of R, where R is a ring. Let R be a ring, and let I1, I2 till In be ideals of R, such that for all I, let me say like this, such that I small I plus I small j, let me use the notations A. Okay. Let me use the notations A. So A1, because I have already used ij's before, so A1 till say An be ideals of R such that Ai plus Aj is equals to R for all ij coming from the set 1 to n and I not equal to j. So we are actually considering a collection of n ideals which are where the ideals are mutually co-maximal. Okay. Then I claim then R mod A1 A2 till An is isomorphic to R mod the intersection of all these ideals I is equals to 1 to n Ai, which in fact is isomorphic to R mod A1 cross R mod A2 cross so on and so forth till R mod An. Okay. So this is what we require to prove. Now this I can actually frame as an equality. I don't need even an isomorphism in this case. I can actually mean this to be equal, because so this is a slight observation that if A1 and A2 are co-maximal, then A1 A2 equals A1 intersection A2. Okay. How was A1 A2 defined? So it was defined as the collection of all finite sums of product of elements coming from individually coming from A1 and A2, right? So let me first prove this, and then we will be moving on to the proof of the Chinese remainder theorem. Now this proof is quite simple. Suppose I choose out an element from A1 A2. So let x be an element of A1 A2. This implies that I can write x as say some r times A1 plus some s times A2, where A1 comes from capital A1, A2 comes from capital A2, R and S comes from capital R. But by definition observe that this is just an element of A1 intersection A2, because R A1 plus S A2, this element will be typically in A1 as well as in A2, right? Clear? Or actually I should write this as, I shouldn't use the terms R and S, I should write this as A1 x is equals to finite sums of elements coming from A1 and A2. So I can actually write this in this way. For example, so suppose I have A1 A2 and I sum out this, yeah, this will follow, sorry. So I have finite sums of these elements, but then observe that what I am trying to exactly imply is that this implies a finite sum. this implies a finite sum. But observe that if I consider the element A2 and I consider the element A1 coming from R, because A1 is an element of capital A1, so A1 can be considered to be an element coming from capital R, then each A1, A2 will be an element of capital A2, because capital A2 is an ideal, right. If you simply observe the element A1, A2, then this will be an element of capital A2, because small a2 comes from capital A2 and capital A1 can be considered as an element of capital R. So because A2 is an ideal, it is closed under multiplication by elements of R, so therefore this is an element of A2. In fact, if I consider the element A1 to be an element from capital A1 and A2 to be an element from R, then this will be an element from capital A1 as well. So the sum of all such elements will also be inside A1 and A2, and hence inside A1 intersection A2. Clear? Therefore this implies that A1 A2 is contained in A1 intersection A2, and this is always there. We do not need the concept of a maximality in this co-maximality in this case. It's always true. The converse needs the concept of co-maximality. So let C be an element of A1 intersection A2, and so C comes from an element of A1 intersection A2. Okay, let me be here. So C is an element of A1 intersection A2. Now A1 plus A2 by definition must equal R, right? But this means that there exists some element x in A1 and some element y in A2 such that x plus y must equal 1, right? Because 1 is an element of capital R. We are assuming R to have a multiplicative identity. Okay. But then observe that, so I choose an element C out from A1 intersection A2, but then observe that I can write C as C times 1, which I can write as C times x plus y, which I can write as Cx plus Cy. And observe that this is evidently an element of A1 A2, because x comes from A1, C comes from A1 intersection A2, therefore C comes from A2. So I have a product of elements inside A1 and A2, and since I also have an element from A1 A2, I mean product of elements each individually coming from A1 A2, and I am having a sum of two elements, hence a finite sum. Therefore this is evidently an element of A1 A2. Therefore A1 intersection A2 must equal A1 A2. Clear? And this happens only in the case where A1 A2 are co-maximal. A1 A2 is always included inside A1 intersection A2, but the reverse inclusion happens only if you are talking about co-maximal ideals. I guess this part is clear. So the actual Chinese remainder theorem in some textbooks is this part only. Let me go back. The actual Chinese remainder theorem comes from this part only, but we can also consider A1 A2, I mean we can also consider this being isomorphic to this directly, right, which we have successfully shown in this case. And we will do that itself, or and we will be actually using both A1 intersection A2 intersection till AN, and then A1 A2 till AN as well. Okay. So what we do is that we first define a map. So the proof of the Chinese remainder theorem. So we define a map phi from R to R mod A1 cross R mod A2 cross till R mod AN. Okay, and how do we define this? We send an element small r to R plus A1 till R plus AN. Now sometimes I will be calling this element R plus A1 or an element of the form R plus AI to be R mod AI, because when we had studied the concept of quotient groups or quotient rings, we have followed that when we choose a representative from certain coset, it actually resembles the concept of taking modulus with respect to that coset, right? And often what happens is that using the term modulus is actually simpler than using the notation of R plus the ideal. Okay, so I will be using both the terms whenever required, but I guess you people can relate. Okay. So now observe that phi is a homomorphism. There's no need of proving this. In fact, this is quite evident from how we have defined it. So since phi is a homomorphism, therefore we know that R mod kernel of phi should be isomorphic to phi of R, right? This comes from the first isomorphism theorem. In fact, observe what is the kernel of phi. The kernel of phi is the collection of all elements small r in capital R such that phi of R is equals to 0, but for it to be 0, it must be 0 in case of every coordinate. But for this to be 0 in terms of every coordinate, if you go by the notion of modulus, it specifically means that R is 0 modulo ai for all I, or in fact this actually means that R is inside ai for all I, but this means that R is an element of the intersection of all these ideals. I is equals to 1 to n, and this is nothing but the product of all these ideals. I is equals to 1 to n. Therefore R mod a1 a2 till an is actually isomorphic to phi of R, right? Now what are we only left to show is that phi R is or rather, let me not use this equality directly here, we will establish recently. For now, let me just keep it to be intersection. Intersection over all these ai's. So what are we left to show? We are left to show that phi is surjective. That will be enough, right? But to show that, see, showing phi is surjective is quite obvious. Once we show phi is surjective, the Chinese remainder theorem is proved. But if I want to prove that a1 a2 till an is equals to the intersection of all these ai's running from I is equals to 1 to n, then I will get the other part of the Chinese remainder theorem as well. But to show this, we can actually proceed by induction. And to show even phi is surjective, it's actually easy to proceed by induction. Okay. So what we do is that we prove that phi is surjective, and this equality is already shown for n is equals to 2. We can indeed extend this to any arbitrary integer using induction. That's quite obvious. We will see that obviously, but we first show that phi is surjective for n is equals to 2. Let us do that first. So let x be coming from a1, y be coming from a2. Since a1 and a2 are co-maximal, therefore I can have x plus y is equals to 1. So I am choosing elements x and y such that x plus y is equals to 1. Clear? But if I choose the elements in this way, that x plus y is equals to 1, then observe that so x is equals to 1 minus y. Now 1 minus y is an element of 1 plus a2, and x is an element of a1, right? Therefore if I find what is phi of x, so phi of x is basically x mod a1 and x mod a2. But observe that x mod a1 is 0 because x itself is an element of a1, and x mod a2 is 1, right? X mod a2 is 1 because 1 minus x is equals to 1 minus y, and y is an element of a2. Hence x is an element of 1 plus a2, so it's typically 1. In a similar way, you can also show that phi of y is equals to 1 0. Okay, and there obviously exists such elements x and y. Now if we choose say we choose an element r1 mod a1, or you can also talk about the elements r1 plus a1 as well. So let me just go by this, r2 mod a2 from r mod a1 cross r mod a2. Then what should be the element such that what should be the element in R which can get mapped to this element, right? If you observe that, what about the element r2x plus r1y? What should be the phi of this? Now phi is a homomorphism, right? Phi is a homomorphism, a ring homomorphism precisely. So it distributes under multiplication and addition. So this is basically phi of R2 times phi of x plus phi of R1 times phi of y. But phi of R2 by definition, it's R2 mod A1, R2 mod A2 times 0 1 plus this is R1 mod A1, R1 mod A2, R1 mod A1, R1 mod A2 times 1 0. But then by coordinate wise addition and coordinate wise multiplication, you will get the element R1 mod A1 and R2 mod A2. And clearly R2x plus R1y is an element of capital R, right? Therefore, we have eventually reached a pre-image of an arbitrary element from the codomain. Therefore, phi is surjective. Therefore, phi is surjective. Clear? Now, observe that if I now choose the collection of elements, let A1, A2 till AN be ideals as given in the hypothesis, be ideals in R, and let Y induction, let the induction hypothesis, I am writing it as IH, the induction hypothesis be that the statement holds for any I less than n. Okay. So if it holds for any I, so by statement I actually mean, what statement I actually mean is that firstly that A1 so A1 A2 till AK is equal to intersection of all these AI's, I is equals to 1 to K, and the map phi is surjective. Okay, this is what I am trying to say. Then observe that the proof is done if I show that A1 and the product of all the other ideals A2 till AN are co-maximal, because the hypothesis holds for this part, because there are less than n elements, and it also holds trivially for this part. So if I show that these two are co-maximal, so I choose this to be A and suppose I choose this to be B, I already have proved the same statement for two ideals. So if I choose B to be the all the product of these ideals, so I eventually land up with only a single ideal. Here I also have a single ideal. I have already proved the above statement for two ideals. So the proof just holds if I just show that these two elements are co-maximal. I hope you got my point. But showing this is actually quite easy, because see, if I choose, see I already have this, that AI plus AJ is equals to R for all I not equal to J, I and J ranging with the provided index. There is nothing too complicated there. So suppose I choose an element out from A1, let us say Xi is an element of A1, let us say Xi is an element of A1, and I choose an element Yi from B. Okay. Or let me not use the term B, let me choose Yi to be an element of any AI, where I is not equal to 1, for example. Okay. I choose this element such that Xi plus Yi is equals to 1. But then observe that this implies that Xi plus Yi is congruent to Yi modulo A1, right? But if it equals if it is congruent to Yi modulo A1, then the product of all these elements Xi plus Yi must be congruent to Y1 till product of these Yi's, simply product of these Yi's modulo A1. But this implies that the elements X2 plus Y2 till Xn plus Yn, the product of all these elements is actually 1, right? It's actually 1, and this is an element from, while this is an element from A1 plus A2 A3 till, and this equivalently proves that A and B are co-maximum, where A and B are already chosen. A and B are co-maximum. Clear? Got it? Okay. So this part is clear, right? Therefore, we have the proof of the Chinese remainder theorem. Clear? Now, observe that a special case to this, or in fact the source from which it actually have arisen in some sort, or at least I can say that the name for this theorem, the source from which the name of this theorem has actually arisen, is simply the fact that Z mod mnz is isomorphic to Z mod mz cross Z mod nz, where m and n are co-prime. So, finding an element modulo m simultaneous, suppose you have simultaneous congruent equations modulo m and n, where m and n are co-prime. So, it is equivalent to finding a solution congruent to mn, congruent to modulo mn. Clear? So, this is actually what we call the Chinese remainder theorem in terms of elementary number theory. One more thing to observe with the thing which I said when I started this discussion, that is this part. Let me just go back once, where I talked about the units of the direct product. Yeah. So, units of R1 plus R2 are the ones where each component is a unit. So, this actually gives us that, let me go back, sorry. In fact, I can also say that Z mod mnz, and I take the group of units of this. This should be isomorphic to Z mod mz, the group of units of this, cross the group of units of Z mod mz. Clear? This immediately follows from the fact that I said that the units of a direct product are the elements which are having units in each coordinates, right? In fact, this immediately gives us a corollary which you can relate more in terms of integers. Corollary. The corollary is that if n is in Z, and I can write n as p1 to the power alpha 1 till pr to the power alpha r is the prime factorization of n, then Z mod nz is isomorphic to Z mod p1 times alpha 1 z cross till Z mod pr to the power alpha r z. This immediately follows from the Chinese remainder theorem. Okay, I guess clear, because see, this is nothing but the ideal generated by p1 to the power alpha 1. This is nothing but the ideal generated by pr to the power alpha r, and n, this is nothing but the ideal generated by p1 to the power alpha 1 till pr to the power alpha r. But observe that each of these pi's are actually distinct, and hence they are co-prime. So, I can relate these two denominators, right? There is nothing complicated here, you can just justify this in language. Moreover, I can say the same about its group of units as well. I can in fact say that Z mod nz cross is isomorphic to Z1 p1 to the power alpha z cross Z mod pr to the power alpha r z cross, right? But then I can actually, so since we have isomorphism, so both sides the number of elements must be same. So, now what are the number of elements in Z mod nz cross? What are the group of units in Z mod nz? It is exactly phi n, but this implies phi of n is equals to, what are the number of elements here? So, in a direct product we have the number of elements to be product of the elements in each of the sets, right? So, this is phi of p1 to the power alpha 1, and it continues till phi of pr to the power alpha r, but this immediately proves the fact that phi is multiplicative, and it actually proves the formula for Euler's totient function. Clear? Okay. So that's all for this lecture. Meet you guys in the next lecture.